In this video, I'll introduce the normal force and then use it in conjunction with Newton's second law. Let's start with a definition of the normal force. When two objects are in contact with each other, the component of the force that is perpendicular to the surface of the object being analyzed is often referred to as the normal force. The key element in this definition is that the normal force is perpendicular to the surface of the object. In fact, the word normal in mathematics means perpendicular. Here's an example of a normal force. In this picture, a physics book is lying motionless on a horizontal table. If we define the book to be the system and draw a force diagram, the table is in contact with the book, so we might call this the force by the table, and then gravity acts on the book as well. The force by the table can also be referred to as the normal force because the table is in contact with the book, and the force is perpendicular to the book's surface. Common ways to show a normal force are either to use a capital N subscript like this, or just to replace the entire vector with an N. Let's calculate the value of the normal force in this situation. If the mass of the book is 1.5 kilograms, what is the magnitude of the normal force of the book? We can solve the normal force with Newton's second law. We've already drawn the force diagram, so now let's write Newton's second law in the y direction. There are two forces in the y direction, the normal force pointing up and the gravitational force pointing down. So plugging those forces into the equation, it becomes this. And we know that the gravitational force is equal to mg, so we can substitute that in. And then solving this for the normal force, we get that it's equal to ma plus mg. As we get ready to plug in values and solve for the answer, the key thing to recognize here is that the acceleration of the book is 0. The book isn't moving, so it certainly isn't accelerating. That means that the normal force in this example problem is equal to mg, the weight of the book. And then plugging in values for m and g, we get that the normal force is 14.7 newtons. A common error that students make when dealing with the normal force is to assume that it's always equal to the weight of the object, as it was in this example. But this isn't always the case. I'll now work through another scenario where we'll learn how to deal with the added complexity of an object being on a sloped surface, and we'll find in that case that the normal force is not equal to the weight of the object. So here's the new problem. A 1.5 kilogram physics book is placed on a frictionless surface with a slope of 35 degrees as shown. Find the magnitude of the normal force on the book and the magnitude of the book's acceleration. Let's again analyze the problem with Newton's second law. The first step is to do a force diagram. The sloped surface is touching the book, and it potentially causes a normal force and a friction force. However, we're told that the surface is frictionless, so there isn't a friction force in this problem. We'll talk about friction in detail in another video coming up soon, by the way. But there is a normal force. By rule, the normal force is perpendicular to the surface of the book, so here it is. We're also told to neglect air resistance, so the normal force is the only contact force. And then there's gravity as well. The gravitational force points down toward the ground like this. And we know that the gravitational force is m times g. Now I'll define the coordinate scheme, but this time I'll rotate it so that the x-axis is parallel to the surface of the slope, and the y-axis is perpendicular to the surface of the slope like this. The problem can also be solved with the traditional horizontal and vertical axes, but when dealing with a sloped surface like this, the math is almost always easier if the coordinate scheme is rotated this way. Traditionally, when the coordinate scheme is rotated, the y-axis is perpendicular to the surface and the x-axis is parallel to the surface, as I've shown it here, but it's actually arbitrary. Now that we've defined the coordinate scheme, the next step is to convert all of the vectors to Cartesian form. The normal vector is in the y direction, so we can write it this way. The gravitational force, however, has components in the x and the y directions, since we've rotated the coordinate scheme. So we need to find its components. The components of a vector are always parallel to the coordinate axes, and the vector itself is always the hypotenuse. With that in mind, we can make a triangle for the gravitational force vector either here or here. It doesn't matter which way you draw it. Given this triangle, here is the x component of the gravitational force, because it's parallel to the x-axis. And here's the y component, which is parallel to the y-axis. To solve for these components, we need to determine an angle inside the triangle. Here's one way to do it. Start with this right triangle. Since the angle in the lower right is 35 degrees, then the angle in the upper left must be 90 minus 35, or 55 degrees. And now recognize that this is a 90-degree angle, so that means that this angle is 90 minus 55, or 35 degrees again. Now that we've found an angle in the triangle, I'll clean up the picture a little. And we can now write down the trig statements for the x and y components of the gravitational force. Plugging in values for m and g, we get values for the components, 12 newtons in the negative y direction and 8.4 newtons in the positive x direction. As an aside, don't mix up the n's that we've used. The n's up here refer to the normal force, and the n's down here are units for newtons. It often happens in physics that the same letter or symbol is used for different purposes, so be aware of the context in which they're used. The next step is to apply the Newton's second law equation in the x and y directions. I'll clear some space and write down the equations. Let's consider the y direction first. There are two forces in the y direction, the normal force in the positive y direction and the y component of the gravitational force in the negative y direction. So putting these into the equation gives us this, and then we can solve this equation for the normal force, where we know Fgy and the mass. But what about the acceleration in the y direction? The physics book will slide down the slope in the x direction, but it will not move or accelerate in the y direction. This is a key observation that allows us to make the y component of the acceleration 0. This, by the way, is why we rotated the coordinate scheme to begin with. It has allowed us to set the x component of the acceleration to 0, greatly simplifying the math that we need to do. And so, since we have already calculated the y component of the gravitational force, we know that the normal force is also 12 newtons, and we have our first answer. Now let's work through Newton's second law in the x direction. The only force in the x direction is the x component of the gravitational force, so the equation becomes this. Solving this equation for the x component of the acceleration, we get this. We can now plug in values, and we find that the x component of the acceleration is 5.6 meters per second squared. As we already recognized, the y component of the acceleration is 0, so the magnitude of the acceleration is the same as the x component, or 5.6 meters per second squared. Well, that demonstrates the normal force and also how to deal with the situation when the object is on a sloped surface. There's also a worked out example on Moodle that should be helpful. We'll continue to work through more applications of Newton's second law in the next few videos.